Okay, here we go on the crash review of Nuclear Chemistry Ride. So, two of the biggest things in nuclear chemistry are nuclear fission and nuclear fusion. And what we need to remember is fission, division. So I'm taking something big, U-235, I'm bombarding it with a neutron, and I'm breaking it into two smaller things. And those two smaller things are usually Krypton and barium. So how can you recognize fission division? Usually U-235 getting bombarded by a neutron and breaking down and splitting into two smaller elements. Fusion, I usually say FU. Fusion, U equals unite. So I take two smaller things, and that is usually hydrogen. Usually it's deuterium. (2,1H) plus 2,1H yielding 4,2He. That's usually one of them. Or it could be 2,1H plus 3,1H yields 4,2He plus a neutron. Either way, in fusion, you've got hydrogen combining into helium. Another important thing to remember is that nuclear reactions generate much more energy than chemical reactions. And the second thing to remember is that fusion is greater than fission in terms of energy. All right. What else do we have to know? There's natural and artificial transmutation. So, natural transmutation is spontaneous, which means it happens by itself. So that means I'm going to start with one reactant and wind up with two products. And in artificial transmutation, that is non-spontaneous. I'm going to start with two reactants because I'm going to bombard something that's completely stable with a high energy particle, and I'm going to wind up with one product, usually. The other thing to remember is that there are radioisotopes that can be used for various techniques. Some of the ones that you should know are I-131, U-235, cobalt-60, and carbon-14. So I-131 is used for thyroid or medical diagnosis. It's got a very short half-life, like 8 days. U-235 is used for geological dating, so rock dating. Cobalt-60 is used for cancer, and carbon-14 is used for carbon dating or fossils. And the other thing that you have to remember is the concept of half-life. Half-life is the amount of time it takes for 1/2 the sample to decay. And we use arrows to represent half-lives. So if I go from 100 to 50 to 25 to 12.5, that's 1, 2, 3 half-lives. So knowing how that works, given certain information in a problem, I can either figure out the half-life, or if I'm given the half-life, I can figure out how much is left. Or if I'm giving a starting and an ending mass and the half-life, I can figure out the time that's elapsed. So it all revolves around knowing what a half-life is and realizing that everything usually starts with 100% at some point in time. All right. We are going to be using tables N and O. So make sure you have them out. Now, I just gave you the nuts and bolts of nuclear. As we go through some of the problems, you'll see how they're solved and you'll see how we use the tables. I may not hit every single type of question, but I will hit most of them. It says the change that is undergone by an atom of an element made by radioactive bombardment with a high energy proton is called what? Well, I told you when we bombard something, it's going to be artificial. Natural transmutation, natural decay, and radioactive decay all mean the same thing. It happened by itself. So that means that I had to have started with something unstable, so it just decayed. But if I bombard something, that means I'm making it undergo change. So that means that it's stable to begin with. Which type of reaction converts one element into another? That's transmutation. Transmutate means to change. Which list of radioisotopes contains an alpha emitter, a beta emitter, and a positron emitter? This is table N. So we go to table N and we look up carbon-14 and we see that it's B-. So here I've got B-. N16, I go to N16 and it's also B-. So right away I know it's not that one. I've got two B-. Cesium-137, cesium 137 is B-. Francium-220 is alpha. And Tectenium-99 is B-. It's not that one. Krypton 85, B minus. Neon 19, B plus. And Rn 222 is alpha. There's my answer. Which nuclear decay emission consists of energy only? That would be gamma. If we go to table O, we can see that gamma particles have no mass, no charge. It's pure energy. The energy released by a nuclear reaction results primarily from the conversion of mass to energy. Which radioactive isotope is used in medicine to treat thyroid? I just went over this with you. It's iodine-131. Which type of reaction occurs when a high-energy particle collides with the nucleus of an atom, converting the atom into a different element? Well, it's technically artificial transmutation, but they don't list that, so we'll just go with transmutation. Which particle is emitted when an atom of Krypton 35 spontaneously decays? This is table N. So I go to Krypton 35, 85, sorry, Krypton 85, and it says B minus. And if I don't know what B minus is, I can go to table O, and I can see that it's beta. What is a problem commonly associated with a nuclear power facility? A nuclear power plant. Well, nuclear power plants, although we didn't go over it in the review, are very difficult to dispose of waste. Which particle has the greatest mass? This is table O. Remember, mass is on the top, charge is on the bottom. If we look at alpha, it says 4,2 He. Beta is 0, -1 E. Neutron is 0, 1 N. Positron is 0, +1 N. So greatest mass is going to be the 4, so alpha. A beta particle may be spontaneously emitted from what? Well, if it's going to be spontaneous, that means that whatever I'm starting with has to be unstable. Which nuclide is used to investigate human thyroid? Talked about that already. I-131 is just another way of phrasing it. Which nuclear emission has no mass or no charge? That would be gamma. This is table O because it says 0, 0, gamma. Which radioisotope is matched with this decay? This is a table N question. So I look at H3, hydrogen 3, and I see that it says B minus, and that's gamma, so that's not it. Potassium 42 says B minus, and that says B plus. N16 says B minus, that says alpha, and P32 says B minus. There you go. Which reaction is accompanied by the release of the greatest amount of energy? So combustion is chemical, electrolysis is chemical, oxidation is chemical, and nuclear fission. I already told you nuclear reactions produce much more energy than chemical reactions. Which nuclides are used to date the remains of once living organisms? That's going to be your carbon family, carbon-14, carbon-12. Energy is released during the fission of plutonium-239 atoms as a result of what? Formation of covalent bonds. That doesn't sound like anything I've been talking about. Formation of ionic bonds. That certainly doesn't sound like anything I've been talking about. Conversion of matter, which is the same as mass, to energy. Conversion of energy to matter. So 3 is the right choice. Atoms of I-131 spontaneously decay when what? Well, it's definitely not stable. Unstable nuclei emit alpha particles, or unstable nuclei emit beta particles. So I look up I-131 in table N, and I see that it is beta. Which type of reaction releases the greatest amount of energy per mole of reactant? So this is chemical, this is chemical, this is chemical, nuclear. Nuclear is always more than chemical. The spontaneous decay of an atom, spontaneous, it's happening by itself. It's technically natural transmutation, but that's not listed there, so we'll just use transmutation. Which type of emission has the highest penetrating power? That's going to be gamma. Gamma is like X-rays, very strong. Which of these types of nuclear radiation has the greatest penetrating power? Same question, asked slightly different. Radioactive cobalt is used in radiation therapy treatment. Cobalt-60 undergoes beta decay. The type of nuclear reaction is called, well, if it undergoes decay, that means it happens by itself, so it's going to be natural transmutation. What is the correct order of nuclear decay modes for the change from U-238 to U-234? Here's U-238 to U-234. The mass number decreased by 4, 238 to 234, and this decreased by 2, 92 to 91. So that's going to be alpha. Then you went from 234, 0, negative 1e, and this is 0, negative 1e. So it's alpha, beta, beta. Atoms of one element are converted to atoms of another element through transmutation. What is the decay mode of potassium-37? That would be B+, beta positive. What's the nuclear emission? Which nuclear emission has the greatest penetrating power? That would be gamma. What is the mass number of an alpha particle? 42He. The mass number is the top number, so it's 4. A nuclear reaction in which 2 light nuclei combine to form a more massive one. Fusion, Fu, unite. Alright, so let's do some half-life problems. If the half-life of Fe59 is 45.5 days, how much of a 2 milligram sample remains after 135 days? So this is my total time. This is the half-life. So if I take the total time and I divide it by the half-life, I'll know how many half-lives have taken place. We're going to round to a whole number. 133.5 divided by 44.5 is 3. So 3 half-lives. So if I started at 2 milligrams, half of 2 is 1, half of 1 is 0.5, and half of 0.5 is 0.25. So this is 1 half-life, 2 half-lives, 3 half-lives. That's what I had to undergo, 3 half-lives. So my answer is 0.25 milligrams. If 25 milligrams of strontium-90 remained after 5 half-lives, how much was in the original sample? Well, I know what I was left with, so I now have to find out what I started with. And I know 5 half-lives took place. And I know that strontium (90) has a half-life of 29.1 years. Well, it doesn't matter because that's kind of irrelevant, because it says if 25 milligrams remains after 5 half-lives, how much was in the original sample? So if I ended at 25, then I double it, 50, 100, 200, 400. So this is 1, 2, 3, 4. So then this has to be 800. And this is 5 half-lives. So 800 milligrams. What is the half-life of polonium-214 if it takes 818.5 milliseconds for 300 grams to decay to 9.375 grams? So first thing I see is I have a starting mass and an ending mass. I want to see how many half-lives took place. I need half of 75. Which is 37.5. And then half of that, 18.75, and then half of that, 9.375. If gallium-68 has a half-life of 68.3 minutes, how much of a 10 milligram sample is left after 2 half-lives? So 10 milligrams, 1 half-life is 5, 1 half-life is 2.5. How long would it take for a 100-gram sample of N16 to decay to 12.5 grams? Well, first of all, we have to figure out how many half-lives took place. So I underwent 1, 2, 3 half-lives to go from 100 to 12.5. So if it's 3 half-lives and they want the total time, I have to know what the half-life is. So I go to table N and I look up N16 and it's 7.13 seconds. So 7.13 seconds for 1 half-life times 3 is going to be 21.39. And that is going to be, what are the units for N16? Seconds. If a radioisotope has a half-life of 2.75 years, how much of a 10-gram sample remains after 4 half-lives? So half of 10 is 5, 2.5, 1.25, and 0.625. So that's 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. So 0.625 grams. Lastly, let's just write a couple of decay equations. So if I said, write the equation for the nuclear decay of Fe59, and I told you that it was beta decay. So this is beta decay. Decay means it happens by itself. We know that Fe, we have to fill in the element, the atomic number. They didn't give us that. So we have to fill in the 26. And remember that we treat the arrow like an equal sign. So 59 is on the left. 0 plus what is 59? This is going to be 59. 26. So this has got to be 27 because that's a -1. And we want it to equal. Then I go to my periodic table and I look up element number 27. And element 27 is cobalt. If I said show the decay of carbon-14, we would go to table N, and we'd see that carbon-14 has beta decay. And therefore, if this is my equal sign, 14, 0 and 14 is 14. This is 6. This has to be 7, because 7 and -1 is 6. And this would be nitrogen. Okay. I think that was a quick review of nuclear.